Hello, today I'm going to talk about chemical equilibrium. This will be my latest chapter. Please remember to give a like to this video and subscribe to my channel for more updated videos in A-level chemistry as well as O-level chemistry. Now, these are the learning outcomes in the A-level syllabus. I will talk about each of them during the lecture. Okay. Now, let's start with this concept on reversible reactions, which is the main theme throughout this topic. So reversible reactions occur in a forward and backward direction, meaning when the reactants react to form the products, at the same time, the products are reacting to form back the reactants. So at any point of time, there is a mixture of reactants and products together. All right. So at the beginning, there's only reactants, but as reaction progresses, we have more and more products. But not all the reactants will react. There will be some unreacted reactants with the products. That is what we call reversible reaction. And we denote it by a double-headed arrow. They are not complete. Rather, we don't say reaction is completed. We say that a state of equilibrium is reached. Now, these are some examples of reversible reactions in the syllabus. They include esterification and the contact process. Now, if you look at A plus B, which are the reactants, we have to form C plus D, the product. We realize that at time 0, which is at the start, A and B are mixed and the forward reaction proceeds to form C and D. So the rate of forward reaction, as we have learned in kinetics, is rate equals to rate constant multiplied by the concentration of A and B, all right? And at the start, we don't see any C and D. As for the rate of backward reaction, it is 0 in the beginning. However, as the reaction progresses or proceeds, we have a decrease in the concentration of the reactants A and B. The forward rate decreases gradually, okay? So it will be the faster at the start, but as reaction progresses, it will get slower and slower. As for the product C and D, at the beginning, they are not present, but when they are formed, we realize that as more C and D are formed, the rate of backward reaction will keep on increase. So the rate of the forward reaction will decrease, the rate of the backward reaction will increase, and it will reach a point where the rate of the forward reaction and the backward reaction will be equal. When this is achieved, we call this state of equilibrium. You can observe it from the two graphs here. We have concentration against time. So at the beginning, we do not have C and D, but their concentration increases, though at a decreasing rate. As for the reactants A and B, they have a high concentration at the beginning, but as reaction progresses, the concentration decreases at a decreasing rate. So the second graph shows the relationship between rate and time. As the rate of forward and backward reaction progresses, it will reach a point where their rate will be equivalent, and this point is the equilibrium. So time at equilibrium refers to the time where the rate of the forward reaction equal to the backward reaction. Now, so at a state of dynamic equilibrium, dynamic means the reaction is still progressing, it's not stopping. When the forward rate and the backward rate is equivalent, but they will never be equal to 0, we have to understand that, okay, the reactions are still occurring for both the forward and backward reaction. And the rate of A and B reacting to form C and D will be exactly equal to the rate of C and D reacting to form A and B. So we are looking at rate of reaction here to see the speed and the progress of the reaction. And at this point where dynamic equilibrium is achieved, we can say that there is no more change in the concentration of both the reactants and the products. They are not 0, but remain constant. So we need to understand that in a reversible reaction, reaction is not complete, and a mixture of both reactants and products will be obtained. In other words, both reactants and products will be present at equilibrium. So this is a concept on dynamic equilibrium. It is a state in a reversible system where the rate of the forward reaction and the rate of the backward reactions are equal but not zero, and there will be no net change in the macroscopic properties like concentrations or partial pressure. All right. Now, these are the features of a system at dynamic equilibrium. Number one, microscopic processes continue, but these are balanced and there is no overall macroscopic change observed. The particles participate in both forward and backward reaction, but the rate of forward processes is equal to the rate of the backward processes such that there is no net change observed. So you will notice that concentration or partial pressure of the species will remain constant. Equilibrium can only be achieved in a closed system. Yes, a closed system. So in a closed system, right, the metal are not allowed to enter or leave. There's only transfer of energy, but there is conservation of mass. There's no loss of mass. So the species are remaining in that closed system, okay, like a closed cylinder, okay, that holds all the gases together, something like that, okay. Moving on, equilibrium is attained from either direction. So you can start with the reactants or you can even start with the product. So it's not necessarily true that, okay, I have to start from the reactants. No, you can actually have the products becoming the reactants. It doesn't matter, all right? Provided the appropriate amounts and making sure that temperature is constant. Because when temperature changes, right, it will change, okay? Equilibrium it will change the equilibrium constant, all right? Now, the same equilibrium state can be attained starting from any amount of reactants and products, provided the temperature remain constant. So there's one important factor we need to consider, that in all these situations, right, the temperature has to be kept constant in that closed system. So we need to make sure that we are talking about closed system where there's conservation of mass and the temperature will remain constant, okay? So T equilibrium represents the time taken for the system to reach equilibrium and is dependent on the forward and backward reaction rate. So when equilibrium is reached, the system will remain in this state until conditions affecting the rate of the forward or backward reactions are disturbed. So you can actually manipulate the conditions and disturb the equilibrium, and a new equilibrium could be achieved. Meaning you could introduce more reactants or more products, or taking away the reactants or products to make changes to the equilibrium system. Meaning you want to have some changes. You don't want it to remain at a constant, value. You want to have some change. You can do it. Yeah, that is flexible to that. Now, let's look at the mathematical expression. So we are looking at reaction quotient, constant, and position of equilibrium. So at any given time, the reaction quotient QC is the ratio of the concentration of the reactants and product raised to the stoichiometric ratio. So we need to look at the mole ratio to calculate or to represent the equation correctly. So reaction quotient equals to concentration of C raised to the power of C. Same for D, A, and B. Okay, so we write this down. So as the reaction proceeds towards equilibrium, QC will change as the concentration of reactants and products will change continually until equilibrium is reached. So when dynamic equilibrium is attained at a given temperature, A, B, C, D concentration will be constant. So QC will be a constant value, and we call it equilibrium constant. So at equilibrium, it will be equal to K. So equilibrium constant K is equals to the ratio of the concentration of the reactants raised to their stoichiometric ratio to the product's concentration raised to their stoichiometric ratio. And we have to be mindful of the units because it depends on the ratio, the stoichiometric ratio, which will affect the units of Kc. So Kc is not consistent. Okay, it is subjected to different expression. Okay. So this empirical mathematical relationship, which relates the concentration of the species in the equilibrium mixture, is known as the equilibrium law. Now, consider the reversible breakdown of N2O4 to NO2. Okay. Now, the concentration of NO2 and N2O4 will change smoothly and continually during the reaction. So does the value of QC. So once a system reaches equilibrium, there is no net change in the color of the mixture. The brown intensity will stay constant. Okay, so of course, it will come to a point where there's no more change in the color of the brown intensity. The concentration remain constant and QC equals to Kc. Okay, so look at this graph here. So at this point, QC is still not equal to the equilibrium yet. Haven't reached equilibrium. So when there's no more change in concentration, that's where the quotient, okay, the QC will be equals to the equilibrium constant. All right. So when QC is still less than Kc, all right, it means that, okay, the forward reaction is favored. Okay, QC is still small, so it means that there is too little products, okay, and there is much more A and B. So reaction equilibrium mixture position is shift more to the right lah. But when QC equals to Kc, that's where equilibrium is attained. The ratio of the reactants, products, or the species will conform to Kc, and the equilibrium is achieved. And when QC is bigger than Kc, that will mean that backward reaction is favored. You have too much C and D, which will react to form back A and B. So reaction proceed in the backward direction to a greater degree. So the relative composition of the products and reactants present is known as a position of equilibrium. So when we come to the phrasing, it will be important for you to write down position of equilibrium. So now these are just some simple exercise. So let's say you have this equation, how to write the Kc and what is the unit. So I just give you the example. Okay, you can redo it again at your own time to practice. Okay, so you can see that, hey, sometimes Kc may not have units. Sometimes. It depends on the expression now, okay? It depends on the equation. But you do have a time where Kc has a very weird unit, like more power 4 dm minus 12, which is very unusual. It's unusual because of the unusual ratio, okay? Now, let's look at the equilibrium constant Kp. Now, Kc is a general term. C means concentration. So if your subscript change to P is pressure, okay, so we're looking at gases. So the method is very similar, just that instead of using concentration, you're using partial pressure here. So, but, okay, let's look at the reversible gaseous system. We have this expression where Pz is the equilibrium partial pressure of gas Z in Pascal. It can also be in kilopascal or atmospheric pressure. So it depends. So there is flexibility, but if the question demands a certain expression, you just have to follow accordingly, all right? So Pz refers to any of the gases in the system. And let's look at an exact example. You have this Kc equals to Hi to the power of 2 divided by H2 and I2. And you write down the expression for Kp, which is equals to partial pressure of Hi to the power of 2 because the ratio is 2. And partial pressure of divide by partial pressure of H2 times partial pressure of I2 raised to the power of 1, since the stoichiometric ratio happened to be 1. Now, so recall partial pressure and Dalton's law from the topic on gaseous state. So partial pressure is the pressure of that gas is equals to the mole fraction multiplied by the total pressure of the system. Or it can be the number of moles of that gas divided by the total mole times the total pressure, which is actually the mole fraction for this one. So this is the mole fraction. And Dalton's law of partial pressure, recall, is the total pressure is equals to the sum of the individual pressure of the gas in the system. Okay, here's another exercise which is similar to exercise 1, where you need to write the correct expression for Kp and getting the right units. Okay, so make sure that when you express the Kp, don't include the bracket. Bracket is only for concentration. Okay, so that is standard like this one. Yep, this is only for concentration, but when we refer to pressure, we just put capital P and the subscript of the individual gases. All right. Now, I think this is what we have gone through. So at dynamic equilibrium, we understand that rate of forward reaction and the rate of backward reaction is equivalent. And we can rearrange the equation to show like that, but make sure that the temperature is constant. All right. So if you recall kinetics, this is how we write the expression for rate equation. So Kf times concentration A raised to power A times B raised to power B equals to Kb, which is the equilibrium constant of the backward reaction, multiplied by C and D. And then you can actually arrange the equation to have the ratio Kf to Kb, and that will actually be Kc. So that's actually how the expression is derived. So it's important to know how is it derived and not just blindly memorize the step, but it's important to understand how this equation was derived. It will be actually better for you to remember. It's easier for you to remember in this way. Moving on, the forms of K for forward and backward. The equilibrium constant of the backward reaction is the reciprocal of the equilibrium constant of the forward reaction. So I think it's quite straightforward lah. So they are inversely proportional in a way. So K forward is equals to 1 over K backward. If you look at from here, you can see why is this like this lah. All right. Okay. Now look at this exercise. Give yourself some time to read and try before we check the answer, okay? You can pause the video. The oxidation of sulfur dioxide to sulfur trioxide is a key step in acid rain formation and sulfuric acid production. So the numerical value of Kc is given below. So this is the contact process where SO3 is formed. Kc was given at 261. There's no unit because of the expression that the units is cancelled off. Calculate the Kc for the backward reaction. So how to do it? So we have the forward reaction Kc. So the backward is just the reciprocal, that's it. But okay, but the reciprocal part is a shortcut lah. But to understand why is it reciprocal is you can write down this expression one more time to understand why the Kc forward and backward are reciprocal to each other. Okay? Now, the form of K. So if the overall reaction is a sum of the two or more reactions, there is this overall equilibrium constant, which is the product of the constant for the step. So let's say there are more than one step, 2 step, 3 step, 4 step, right? So the overall equilibrium constant is just the product of the individual K lah. So that's to let you know lah. All right. So let's say you have this exercise. Nitrogen and oxygen react to form nitrogen dioxide. Okay, so these are their numerical Kc, the individual steps. So assuming at same temperature, so you know if the temperature is constant, right, then there is no change in K. So if you combine these two equations, it will be like this. Okay, the NO is cancelled off. It's because it's an intermediate product. So in the second step, it was used up already. All right. And how do you do this? I mean, you just have to multiply. That's it. But this is the understanding how to get it lah. Next, when the Stoichio coefficient of a balance equation are multiplied by a factor, then k is raised to the power of the same factor. Okay, let's try an example. So it's easier to understand from the example for this one. So you have a numerical value of Kc for ammonia formation is given below, blah, blah, blah. Okay, now if we change the coefficient of the equation, which we will call the reference equation, okay, what will be the numerical values of Kc for the balance equations? All right, so let's look at it. So you have this. Okay, so to do this, sorry, I haven't showed the question yet. So if we change it to divide by 3 throughout the equation, how will that change the Kc? So that's what it means lah. Okay, then you have to make sure that, okay, so all this will change lah. So instead of like NH3 to the power of 2 over N2 times H2 to the power of 3, right? It will be something like that. It will be changed. Yes, it will be changed. So you will do something like this. And then just do some mathematics lah. Then you just bring out 1/3 lah. It's the same lah. Okay. Then you realize that, the difference is just 1/3. So 2.4 times 10 to the power of -3 to power 1/3. That's it. Yeah. So you can just take out the common factor to make this, meaning the one in the bracket, right, is the original equilibrium constant expression. Okay, so whatever Kc that was given, you just raise to the power of the common factor. That's what you call of the same factor. They call it multiply by a factor. Then if you have something like this, it's the same step. But this time around is, I think it's the other way around, the backward reaction. So it's just, you notice that they actually divide by 2 throughout. So you just minus half. It's minus because it's reciprocal. Yeah. Now, let's look at those factors that will affect equilibrium constant. So recall Arrhenius equation, okay? So Arrhenius equation states that K equals to A E minus EA over RT, okay? Now, since the rate constant Kf and Kb are independent of concentration or partial pressure, but they are dependent on temperature based on Arrhenius equation. Kc or Kb is constant at specific temperature, but varies with temperature. Okay, so the values of Kc and Kb is not affected by, number one, the change in concentration of reactants and products. So you can remove or add reactants and products to the equilibrium system. There will be no effect on the expression K, the value of K. Even you change the total pressure, not a big deal. Whether there's catalyst or not, no big deal. So just take note. Because based on Arrhenius equation, it's only affected by temperature. Okay? Now, what is the significance of equilibrium constant? So how far does a reaction proceed depends on the magnitude of the equilibrium constant. So equilibrium constant gives you some information about the extent of reaction, whether the reaction proceed more towards the reactant side or the product side. Okay, so for example, okay, you look at this, you have a value of K that's very small. What does it mean? It means that very little products form. In other words, this reaction with this K favor the reactants more. So if the K is very small, the position of equilibrium lies very much to the left. This is how you write it, okay? Very small, position of equilibrium lies to the left. You must say lies to the left. And to a certain extent, right, you can say there's almost no reaction to the right. Almost. But I would prefer to say that position of equilibrium lies very much to the left. Okay, I'll prefer that. Now, If you have the opposite, oh, very high K, it means that not much reactants present at equilibrium. Or in other words, the reaction really favor the product side. So if K is very large, how do you say it? Position of equilibrium lies very much to the right. So it's almost a completed reaction. If you have something like 5, it means that, okay, in between, significant amount of reactants and product present equilibrium. So this is how you phrase it. Intermediate value of K, significant amount of reactants and product present. So in summary, the expression must be accompanied by the chemical equation of interest, as it is very sensitive to the stoichiometric coefficient. So if you change the coefficient, then that's what we see just now. It will really change K. So the units of Kc and Kb will also vary with the stoichiometric coefficient. So Kc or Kb is only affected by changes in temperature. It is not affected by changes in concentration or partial pressure. The position of equilibrium shift such that the equilibrium concentration will give the same numerical value of Kc or Kb. The magnitude of Kc or Kb does not give any information on the rate of forward and backward reaction. No, please do not think that way. It doesn't. It just tells you the extent of reaction. It doesn't tell you, oh, the rate is faster. No, you have to look at kinetics already and not looking at this. All right. Homogeneous equilibrium refers to a system where the substances are in the same phase. Okay. It's just an example for you to refer to it. Heterogeneous equilibrium refers to a system where the substances are not in the same phase. So let's consider Kc expression for the decomposition of calcium carbonate. Okay, so in this case, like its density at a given temperature, we need to understand that, okay, concentration of pure solid at calcium oxide and calcium carbonate, they are always constant because the particles are held in a fixed position, meaning they have the same number of particles per unit volume and it's fixed. So that will be, it cannot have any change, in concentration of that. No way, because they are not like in equal state, they can, no, they are fixed. There's no change in the number of particles per unit volume because the particles in solid are held at fixed position. They cannot move around freely. Okay, so that's the idea. So you can just rewrite the expression here to make it into, okay, you shift the CaCO3 here, CaO below, you get Kc times CaCO3 over CaO. And you can rewrite this whole thing, because these two are solid, into a new equilibrium constant. Because these two, right, are constant, so you can multiply with it to form a new constant. So we have a new equilibrium constant that is inclusive of the concentration of the calcium carbonate and calcium oxide, which are solid. Okay, because their concentration of pure solid always be the same. So you can rewrite it to be Kc is just equal to CO2. That's for heterogeneous equilibrium system. Now, another example, let's say you have, or you can actually write this in terms of, instead of concentration, you can write in terms of pressure, equilibrium constant in terms of pressure, then vapor pressure of solid will be constant, of course, because it's not vapor. So these two will be constant, and you can just combine these two with Kb to form a new expression for equilibrium constant, and then it's just like that. Okay, so in summary, right, Kc and Kp are expressions of heterogeneous equilibrium that won't include the concentration and partial pressure of pure solid and pure liquid, because their concentration of partial pressure, right, will be always constant at a given temperature. So concentration is actually number of moles divided by volume. Number of moles is mass divided by molar mass. And then if you divide this expression, you will find that M over V is density. Density over molar mass. Density is constant for solid and liquid. Okay, because Yeah, because of the nature of how the particles are arranged, right? So they will always be constant. So this is the understanding lah, okay? The conceptual understanding. And also because water is present in very large amount, because it is used as a solvent, it has to be large amount in order to be able to dissolve the solute. So water concentration is constant. Anyway, this is you can just use this expression. You realize that it is fixed at 55.6 mole per dm cube. No change. Now, here are some examples. You can refer to them. Write down the Kc and Kp expression. Now, this part is just to revise the understanding that you just treat solid, liquid, and water as constant, their concentration or partial pressure. So in this case, we just care about the gas here. We ignore the I2 solid. It's part of the constant now. It's part of it. Kp. Then with this one, I think just these two. Yeah, correct. You ignore this one. Not ignore, but just don't write it down. Then for this one, you just don't care about this. Don't care about this one. So you just have H2 and H2O. All right. This is not correct. It should be here, minus. Okay. Next. Then you have this one. I think can just ignore this one. And this one is just this one. It's 1 over Cl2 because Cl2 is the reactant. Then this one, you just ignore this one. You just 1 over H2OG. Then another example to reinforce the understanding. Just ignore. Cannot ignore everything. You know why? Water is the product, not the solvent, so must be included. Water here is not the solvent, it's the product. So it is not in large quantity. Okay, so not in large quantity. It's not a lot. So as long as it's not a large quantity, cannot work. Okay. All right. Wow. Okay, let's do some calculations from involving equilibrium constant. So let's look at this example. When you have 2 mole of HI dissociate in 2 dm cube vessel at 440 degrees Celsius, you have only 1.7 mole of HI left. Calculate the Kc. Okay, fine. That is a standard way of doing it. So I'm going to teach you this strategy. It's called the ICE method. I stand for initial, change, and equilibrium. All right. So you can do a simple table. You don't have to draw the lines. You can write down the equation with the ratio 2HI, H2, I2. So I'm going to show you the step. So every time you just do this. Okay, very standard. So they say that HI has 2. Okay, H2, I2 initially 0. Then what is the change? They say that 1.7 left means at equilibrium, you have 1.7, which means that it lost 0.3. If you lost 0.3, this one will gain 0.3 divided by 2. Not 0.3 because this is half of this, so you must divide by 2. Same for here. Then after that, you rewrite the expression as this. The reason why you divide by 2 is because the volume is 2. So this one is mole, but this is concentration. So you need to divide everything throughout by 2. Understand? Yeah, then you get this expression. Be careful. This is in terms of concentration, not mole. You must consider the volume. Okay, next. And in this case, the Kc should have no units because cancel off already. Now look at another example. You have 1 mole of methanol and ethanoic acid. Esterification. So the equilibrium mixture will have 0.2 mole each of methyl, ethanoic, and water at room temperature. Calculate Kc. 2 moles of methanol and 2 moles of ethanoic acid were mixed together at the same temperature. Calculate the amount of methyl ethanoate produced at equilibrium and calculate the percentage yield of the ester under these conditions. So how to do this? Again, ICE, please, always ICE. ICE method. Okay, so because they give you more, you need to divide by V. But I don't know what is V, but you know that it is the same volume because these two share the same volume. So they have the same volume, divide by V, divide by V. So this two is 0. Then they say that at equilibrium, so normally, right, the ICE, right, the E actually comes before the I. Yeah, normally. So you have, they say what? You have 0.2 methyl ethanoate is this one. So you got 0.2 divided by V. Then the other one, the water is the same mole ratio, so also 0.2 over V. Okay. Then it means that the change is plus 0.2 over V plus 0.2 over V, which means that these two, right, loss minus 0.2 over V minus 0.2 over V. So because everything is equimolar amount, so this one plus how much, this one minus how much, and then you just calculate to get this one. Then write this down. Then this one should have no units also. Yep. Try again. So part 2, sorry. Part 2 says that, okay, there's a part 2. You have 2 mole of methanol and 2 mole of ethanoic acid. Calculate the amount of methyl ethanoate produced at equilibrium. Okay, so let's do the second question. Now you have 2 mole, then okay, now you have calculate Kc, you can work backward to find out. That's the thing. So initially got 2 mole divided by V. But you know that you don't know how much it actually lost or how much here gain. So here you put X X as the unknown. Okay, the unknown, the amount of mole that methanol lost, which is equivalent to the ethanoic acid, and it's the same as the methyl ethanoate and water. Then you just write down using IC method. IC method really very powerful. Then you do this, then you know that this is equivalent 0.0625. So if your previous answer wrong, then forget it, it will be wrong. Okay, so it's actually algebra because I'm sure you know how to solve quadratic equation. So you do this, then you will come to it's very mathematics. The V will be cancelled somehow because same the V cancel. It's just left with X as the only unknown algebra. Of course, you reject minus 0.25 Then you get 0.4. So X is 0.4. You will get 1. Wait. Oh, 0.4 correct. So you get 0.4 mole divided by 2. So the percentage yield will be 0.4 divided by 2. So actually, so the number of moles of methyl ethanoate at equilibrium will be 0.4 mole. But this is, you divide by the, percentage here is how much was actually produced, divide by the expected yield, correct? So expected yield is 2. So times 100% give you 20%. Yeah. Why is it 2? Because you see, you know why 2 or not? It's 2 because you are given 2 more and 2 more of this So the mole ratio is 2, so expect to get 2. But you know percentage cannot be 100%. Anyway, it's reversible reaction. Yield will be even lower. Now, okay. Let's look at this for example 3. Another question. Okay, look at it. You can pause the video. First, the gaseous equilibrium mixture in a flask at temperature T was found to be consist of 0.5 mole SO2, 0.12 mole O2, and 5 mole of SO3. The pressure was 800 kilopascal. Calculate the partial pressure of the 3 gases in the flask. So how to do it? Number 1, just find the partial pressure first. You know how to find it, right? You just take the mole fraction times the total pressure, which is 800 kilopascal. So the the number of moles of SO2 was 0.5. You divide by the total number of moles times 800, then you get 71.2 kilopascal. Pressure of O2 is the same, 0.12 divided by the total mole times the 800 kilopascal. Then same for SO3. Then this will be the, you get one tick. Okay, next one. KP, okay, so just there is no need to do the ICE method because they already say that at equilibrium, this is the number of moles. Okay, so make it simple, huh? No need, huh? So you just have to plug in correctly. Be careful of the coefficient, okay? I think they never really be careful of the coefficient. So you have to write the equation. If you don't write the equation, how you know the mole ratio? Right? Yeah, you have to write yourself. Okay, and balance the equation. Then you solve this off. Make sure the units is correct. The units, if they never specify, just give whatever they give. Save time. Don't need to convert. Don't waste time. Next is another word example. Can we get Ricky and pause the video? Okay, they said that at this temperature and at this pressure, Newton per meter square is pressure. Okay, you have 84% dissociated. Okay, calculate the KP. If 84% is just, you can just solve it by IC method. Yes, because you do not know at equilibrium what happened. Yeah, so you need the IC method. So ICE, so you let X be the mole of the initial amount. Because I don't even know what is it at the start, so I let it X lah, okay? Then I know that it's 84% dissociated means minus 0.84 lor, because 84%, if this minus 0.84, same mole ratio, right? This one is plus 0.84 plus 0.84. Then at equilibrium, you have 0.16, then just add, and then you calculate the total amount of gas first. So add. Okay, you get 1.84. You know why? This is amount, not pressure. I need to find KP in terms of partial pressure. This is not enough. You need to do the partial pressure calculation. Okay, Dalton's law. Okay, so there's one extra step. Be careful. It's amount, not pressure. So need to convert. So after that, you take 0.16 divided by 1.84 times the total pressure they give you. Do it for the same for SO2 and Cl2, which is the same line. Okay, and then you just calculate. That's it. Okay, another example. So I'm giving all the types that will come out already. Okay, everything that will appear. Okay, read this first yourself. Okay, now I'm not going to read the question for you. You read yourself. Okay, how to find the partial pressure? They give the KP, so you use the KP to work backward. So to do this, let X lor. So every time you have, okay, in the question they ask for certain thing, right? That thing become the unknown lor, if that's easier for you to get it. So in that case, X is the partial pressure of NO2 at equilibrium. So the initial pressure was 0.5 atm. It becomes X. That's what they say. Then, so for part 1, to find the partial pressure, you just have to use the KP at this condition. So PP equals to 0.725 equals to X squared. Why X squared? Because it's 2 ma. Divide by 0.5. Then you solve lor. Next question, final pressure of the system. Total pressure, you mean? Just add lor. Nothing much. Just add this. But if this is wrong, this is wrong. Too bad. Okay, now, calculation involving degree of dissociation. Sometimes in question, they will use that term. So either they say, like just now that one, there's this thing, percentage dissociation. Sometimes they will use the term degree of dissociation. It's very similar to that. So, some gases undergo dissociation where they break down to form smaller gaseous fragments like this. So at equilibrium, the equilibrium mixture will contain both the undissociated gases and gases which has been dissociated into. The total number of gaseous molecules is greater than present before dissociation. So degree of dissociation is the fraction of reactant that has dissociated. It can be expressed as a fraction or percentage. So the degree of dissociation is equals to amount dissociated over total initial amount. So as temperature increases, the degree of dissociation will increase. Okay. In this case, because you have more moles on the product side, so the total number of gaseous molecule will increase upon dissociation. So let's look at this example. You have N2O4 becoming NO2. The total pressure is 2 atm. Is 35% dissociated to NO2. Calculate Kp. So ICE again. So always ICE. Initial. This time around, the unknown be A, the initial amount. Okay. I don't know how much. 0, total A. Change in amount because they said 35%, so minus 0.35. This one times 2, 0.70. Then after you calculate, then total is this one, right? After that, not in this amount, not pressure. So you need to convert to pressure. After that, you times 2 because total pressure is 2. Then this is the respective partial pressure. Okay, so I have to do all this table thing lah. Then after that, you just calculate. Okay. Another method is you just directly put in terms of pressure. I mean, that is more, but the troublesome part is I still have to convert to pressure lah. Okay, up to you lah, depending on what you prefer lah, okay? So you can just, this is actually shorter. Yeah, shorter. So you have P0, then they say 35%. Pressure and mole are proportional. Yeah, mole, partial pressure and mole. After that, minus 0.35 times 2. Then after that, it's just 1 minus this by 0.65, 0.70. Then add together is equal to 2. Then you can find what is P. And then, yeah, you just have to sub in here to get the answer. Okay, can or not? Okay. Because they give you the total pressure, but P is not 2 hot. P is the initial pressure N2O4. Yeah. Then the next question asks what will be the degree of dissociation? Okay, now you change the pressure to 1. Okay, fine. So you have B. Now the degree of dissociation become the unknown. So you let the alpha be the degree of dissociation. 1 minus alpha times B. 2 times alpha B. Total pressure, total equilibrium amount is this plus this equal this. Yeah, mathematically lah. Okay. Because alpha minus plus 2 alpha become plus alpha. Okay. Equilibrium mole rate fraction. 1 minus alpha. Equilibrium mole fraction is this divided by this. So you cancel off the B. Yep. No. This divided by this, sorry. This divided by this. So the B is cancelled off. Okay. Same for here, this divided by this. After that, you have to find the mole fraction because I need the partial pressure lah. Okay, and then I will just, because now change to 1 atm in the second question, if you recall. So you times the mole fraction times the total pressure, give you the partial pressure. Then you just have to sub in here lah. Yeah. This 2 alpha over 1 plus alpha power of 2 divided by 1 minus alpha plus 1 over alpha equals to 1 point. So you solve this. The value of Kp will be unchanged because in the question, right, they never change the temperature wall. So the Kp is the same. So equate that to 1.12. You find alpha, and that's it. But you may not know how to get this expression. 1 minus alpha. Yep. Next one. Gibbs free energy and position of equilibrium. So in the previous topic on energetics, right, the concept of using standard Gibbs free energy change help to predict if a reaction is feasible. Now, GA and GB are absolute standard Gibbs free energy of pure A and pure B. So the change in Gibbs free is equals to B minus A and represent the difference in standard Gibbs free energy of pure A and pure B. We can use this difference to predict whether the complete conversion of A and B is thermodynamically feasible. So the delta G is the instantaneous gradient at any point along the curve. So this is the reversible system lah. So what happened is that the change in G is the gradient, then it will go down. So the more negative, then it's the more feasible, right? Yeah. So this is the equilibrium, something like that. So this is pure A. So towards as reaction proceed to form B, the Gibbs free go down towards B will go up again. Equilibrium is somewhere in between. Okay, in a reversible reaction or system, the reaction is not completed. We will have a mixture of reactants and product. So in this context, right, the mixing of A and B will result in increase in entropy and a decrease in Gibbs free. That's why the value of G when equilibrium is reached is lower than A and B alone. This corresponds to the lowest point. Okay. The value of G, right, when equilibrium is reached, must definitely be lower than A and B when it's pure. Because the more negative, the more favorable. So equilibrium is the most favorable conditions. So under constant temperature and pressure, the reaction mixture will adjust its composition such that Gibbs free energy is a minimum. The change in Gibbs free is therefore the derivative of Gibbs free energy with respect to the composition of the reaction mixture. So on the curve above, delta G is the instantaneous gradient at any point along the curve. The value of delta G can be used to predict if a reaction is spontaneous at a particular composition. So if delta G is less than 0, here, forward reaction tends towards the equilibrium is spontaneous. Rate of forward reaction will be faster. So we use Gibbs free to predict the rate of reaction, which is faster, which is actually slower. Okay. Okay, take a look at this. Okay, I think I will just pause here due to lack of time. I thought I will only take 1 hour to complete, but I think I need to take 2 hours. So I will continue with part 2 tonight. Thank you.